Hey everybody, it's Mr. Carr again. Today we're going to be looking at 3.5 day 2. We're going to continue with our modeling with nonlinear regressions, but we're going to be looking at one specific model today, and that is going to be called the logistic growth function. So that's this function right here. So f of t equals c divided by 1 plus a times e to the negative bt. So a, b, and c are my parameters. T is just usually with our modeling types of equations, it's going to represent time. So that time could be different depending on what you're analyzing there. Okay, but A, B, and C are all constants that would go in for those values. Now C has a special job. And let's take a look at the curve to help us see what C does. So logistic growth almost looks like an exponential growth if it was going to continue on like this. But a lot of real life scenarios does not allow for continuous exponential growth forever. Okay, so because of that, we have some kind of a limit. So a lot of real life cases will actually have this idea here where it goes, increases, but then it levels off. This is what's called C. That is representing the limit to our growth. It has a special name called carrying capacity. Okay, so that C value, whatever it is in the top of that function, C divided by whatever, is representing the oops, I did that wrong. It's not carry capacity, it is carrying capacity. There we go. So it's the carrying capacity. Okay, so it acts just like an asymptote. The graph will increase and it'll just slowly approach the value of that carrying capacity, but it cannot actually reach it exactly. So let's take a look at our scenario that helps us with that. So the number of television ads for a certain product affects the percentage of people who purchase the product as shown in this table. Use a logistic regression to find a logistic growth function to model the data. Then use your model to predict the limit to the percentage of people who will purchase the product. So you can do this in TI-84 graphing calculator. I'm going to do it in Desmos. But if you do it in your calculator, just make sure that after you put in L1 and L2, you would click stat, arrow to the right for the calc, arrow down until you get logistic. This is the version. So like instead of, it won't say logistic regression, it just says logistic. Okay. So for me, I'm going to do this as X1 and Y1, and let's go to Desmos to see what that looks like. So that's this graph right here. So you can see how it is curving up, but we're claiming that it's going to have a limit to it. So in this scenario, here's my regression equation. I'm typing it exactly the way it showed on the previous page. C divided by 1 plus A times E raised to the negative BX1. So instead of T, I've got X1 in this position. When you type out this exponent, like you can put parentheses around the negative BX1 or just leave it like this, doesn't matter. Okay. So now I have that there. You can see how the curve is going on that one. And you see my three parameters for A, B, and C. You got 55.8611, 50.2402, and 0.064. Okay, so let me go ahead and write those into my model. So Y is equal to 55.8, we'll just go 86, divided by 1 plus A, which was 50.24, times E raised to the negative, that's going to be 0.064. Oops. 0.064, and then X. Okay, so that is my logistic model. So I could, if I wanted to, start plugging in different values of X. Now notice X in this case is representing ads. Our original function represents T, but we don't have T here really. We don't have time. We have number of ads. Okay, so the idea according to this model is that there's going to be a limit to how many people buy the product. Okay, so based on this, we can look at it and just figure out the carrying capacity, which is this number here. So according to our model, the limit of 55.86% of people will buy the product. Okay. So even if we can keep going with a lot more ads, the more ads we get, eventually it's just going to level off. It won't go on forever and get 100% of the people. So that's our logistic model there. The other main thing we want to be able to do with this is choosing regressions. So in this unit, we've talked about exponential, we talked about logarithmic, and now we talked about logistic regression. So what we want to do here is we want to determine a regression equation that best relates the profit of a website. It has the profit of a website with the time it has been in business. Then determine the approximate time it will take for the website to earn a profit of $1,000 in 1 year. So this is our profit given each of these years. So the first thing we want to do is we want to use our X1, Y1. I'm going to go ahead and put those into Desmos. Well, actually, sorry, I'm not going to do X1, Y1 because I've already got set up with X2, Y2. Okay, so when I go to Desmos now, we can get rid of these other ones. So here's X2, Y2. Okay, now with Desmos, if you just keep adding more tables in, it'll just automatically make it X3, X4, and so on. So I've got X2, Y2 because I already had my previous table. So based on this, you look at the curve, you kind of look at that behavior. What is happening overall? It looks like I have exponential growth. Now, that means I'm not going to deal logarithmic ones. Usually logarithm is going to kind of go down with the way we have it set up for our logarithmic regression. So I don't think logarithm is going to fit. But I think exponential or logistic might work, but based on this, we're talking about the profit. I don't necessarily think that there has to be a carrying capacity to profit. So that's why I'm going to use the exponential regression here. So when you type this into Desmos, make sure you're referring to X2 and Y2 in your equation. So if you remember from that, it's going to be Y2 is approximately equal to, so we'll do this one. It's going to be A times B, and then B is going to be raised to the X2 power. Okay, don't forget, you're going to want to plug in or click the log mode and make sure that's set up on there. And then we can look at our parameters. And that looks pretty good. Okay, so it looks like it's, well, not just pretty good. Like with that R squared being 1, all the data points are on this curve. Okay, and again, the idea is that look at that behavior. Does it seem like it might be like tailing off at the top, or is it just going to keep growing? In this case, I think it's going to potentially just keep growing. So based on that model, we have everything we need. It's going to be 1,000, and then B is 1.78. So here's my regression model that I'm choosing. Y equals 1,000 times 1.78 raised to the X power. Okay. So now the goal is, when is it going to reach $100,000 profit? So we want to figure out what X value is going to create this. There is an algebraic process to solve that. I'm not going to do that one though, because I'm just looking for an estimate. So let me go ahead and go back and figure out where it is based on the graph. So we want to go to 1,000. One easy way to do this is if Y is 1,000, I'm going to just graph this horizontal line right here. But then I got to scroll up until I get to $100,000 right there. So now it's just a matter of looking at when do those two lines cross. So this is just one option. You can also go to the table and just figure out when does this new equation cross over, like especially if you're using TI-84. But I like doing the intersection point. So it happens at 7.987 years. Okay. So X equals 7.987 here. So to answer the question was that how long will it take? It'll take about 8 years for the profit to reach $100,000. There's my full answer within context. Okay, so that is it. Make sure that we understand how to type it in for the logistic model. But outside of that, also being able to look at our data points and figuring out what do you think is the best fit, and then applying that and doing that. Sometimes it might work. You might have to do multiple equations in the same set of data just to make sure. But for the most part, you should be able to look at the behavior of your scatter plot and see where it goes to make your choice off that. All right, that's it for today. Take care, everyone.